Hi, Tom the Professor here. It's time for another problem. Let's get started. The problem for today's episode doesn't come from a textbook. Instead, it comes from a video that I saw last week. The title of that video is Atlas Stone versus Bulletproof Glass from 45 meters. It's put together by the guys at How Ridiculous. I will leave a link in the description to their video if you want to check it out before you tackle this problem. Now, as I was watching the first impact with the ground of the Atlas Stone, I started to wonder, what is the impact force? Because that's how my mind works. So I came up with this problem. I will put the text up on the screen. And I'm going to be using the same method I used in episode 1 to solve the problem. But I'm not going to go through that method exactly the way I did in episode 1. If you need a refresher on what I'm doing and how I'm doing things, check it out again. It's a great watch. So we'll start with, what do we know? From the description of their video, the mass of the Atlas Stone was 70 kilograms, and they drop from a height of 45 meters. The first impact is directly with the ground, and it looks like it buries itself halfway up the Atlas Stone. So I needed a diameter for that Atlas Stone, and I found a value online of about 45 meters. Of about 40 centimeters. Give or take a few. It looks like it buries itself about halfway, so we're going to use a stopping distance of 20 centimeters. What we want to find is the force at impact. A lot of the time when you have an impact, you will be looking for the energy of impact, but I wanted to take it just a little bit further and look at how much force is being applied by the ground to get that stone to stop. Now, anytime you have a force acting over a distance, work is done. That's how we define work in physics. As long as the force and the distance are in the same direction, that force does work. The ground is going to be doing the work to stop the stone in this case, but we can get information about the force from the work definition here. We do know the stopping distance, but we don't know what the work is. So there must be another way we can find work. Okay. Is there another way we can find work? Yes, there is. Work is also equal to a change in energy. In this case, it's going to be a change in kinetic energy. Right before the stone hits the ground, it has kinetic energy because it is moving. That kinetic energy is going to go to 0 because the stone stops eventually after that 20 centimeter impact with the ground. So there's definitely a change in kinetic energy. We just need to then find, what's the kinetic energy before it hits the ground? Okay, let's go back to our picture here. We're looking for the kinetic energy just before it hits the ground. That occurs down here at the bottom. The kinetic energy and the gravitational potential energy are 0 after the sphere comes to a stop. There is a little bit of fudging going on in that gravitational potential energy because I'm leaving out a 20 centimeter distance for gravitational potential energy. But we're dropping from a 45 meter tall tower, so that 20 centimeters we'll just throw in the error bars. It's not going to make that big a difference. At the top of the tower, the sphere is going to start from rest, so it doesn't have kinetic energy. It has gravitational potential energy. And that gravitational potential energy is going to depend on how high the tower is. As the energy falls, it is not destroyed. It is changed from potential energy into kinetic energy. It is conserved in that way. So we're going to use conservation of energy for this problem in order to calculate what the kinetic energy is right before the ground. And then we can use the work energy theorem in order to calculate the work done by the change in energy. And then from that work, we can find out what the impact force is. So let's go to our possible solution here. Energy is changed from gravitational potential energy to kinetic energy as the stone falls. So let's write out the conservation of energy. In general, in an ideal case, it looks like this. The kinetic energy at the start plus the potential energy at the start, in this case before the event happens, which is the dropping of the stone, is equal to the total energy after the stone falls, the kinetic plus the potential energy at the end. Now, since we're starting from rest, the kinetic energy at the start is 0, so I can zero out that term right away. And I can conveniently set my potential energy at the end to be 0 anywhere I want it, so let's put it right before it hits the ground. Our equation then becomes the kinetic energy is right before it hits the ground is equal to the potential energy we start with. We calculate that potential energy by taking the mass of the stone times the acceleration due to gravity times the height from which we're dropping it. So that's 70 kilograms times 9.8 meters per second squared times 45 meters to give us an initial value for the energy of 30,870 joules. Back to the work equation here, and we got force times distance is change in kinetic energy. The final kinetic energy is going to be 0 because the stone comes to a stop. The initial kinetic energy is going to be how fast it's going right before it hits the ground, which is the value we just calculated. So I throw those two values in there. Stopping distance, I change from centimeters to meters. And then we'll divide that out to get the force, and we get a value of 154,350 newtons, which translates into 34,700 pounds for those of you who are not used to the metric system. Now, as you see in my picture over here, that's the net force acting on the sphere as it stops. Now, I compared the two forces acting, the force of the ground and the weight of the sphere itself. The weight of the stone is only about 600 newtons. So compared to the net force acting, I said it's insignificant. So I'm not going to include it in this value. It would just add an extra step into the calculation, but I'm not going to go there. So here's the force of impact. Let's collect all that information in our nice template, and we will celebrate. So we start with, what do we know? The mass is 70 kilograms, height 45 meters, stopping distance of 20 centimeters. We're looking for the force from the ground to stop the stone. And in our possible solution, we start with the work energy theorem. We don't know the kinetic energy, so we switch to conservation of energy in order to find that kinetic energy. And once we have those values, we plug them in to get our description, to get our answer. Well, that's it for this problem. If you liked it, like. If you want to see more, subscribe. You can get me at my social medias at Tom Teaches Physics for both Facebook and Twitter. All of these crazy ideas I write down somewhere, and a lot of them show up in my blog at tomteacheспhysics.com. I've been doing that blog for more than a year now. There's not a lot of posts there, but, I've been busy. I also finally have some merch to go along with that, so check out the links in the description to merch if you're interested in that sort of thing to help support the channel and the blog. I'll see you next time.